Okay, Chem 1110 students, we are to the last video of Chapter 3, talking about the electronic structure of atoms. All of what we use now is based on that Schrodinger equation that says electrons can act like waves. And although the mathematics is fairly confusing, very high-powered math, the results truly explain how atoms interact to form molecules, and molecules go on to form chemical reactions. So we're just going to pursue this a bit further. I mentioned once before that once you have more than one electron in an atom, that things get much more complicated. And in this case, you can see the hydrogen emission spectrum has more lines than the hydrogen, and this is due to the fact that it has two electrons, and this behavior was not well described by Bohr. So in Schrodinger's equation, what it shows is that when you have multiple electrons, the energies of those atomic orbitals split. So you'll see I have not drawn the 2s and the 2p orbitals all on the same line. Furthermore, if you look at the 3s, the 3p are higher and the 3d are much higher. In fact, they're higher than the 4s. This is borne out by the chemical behavior that we see in the periodic table, and we're going to take a further look at that. But there's this little memory aid that's shown here on the right to help you remember how electrons fill into these orbitals and which ones have the highest energy. So I've written them so that you know the principal quantum numbers are in a row. We have 1s and then 2s, 2p, and then 3s, 3p, 3d, but we know those have different energy levels. All right, the first rule is that the electrons will always go into the lowest possible energy level because nature finds that the lowest possible energy is the most stable. Remember, each orbital can only accommodate 2 electrons because electrons repel each other. They're both negative charged. However, the fact that they spin and create a magnetic field, one where it's as though the North Pole is down and the other where the North Pole is up. And since North and South attract one another, that magnetic attraction overcomes the electronic or electrostatic repulsion. The other thing that we talked about is that empty bus seat rule. Electrons will not pair in degenerate orbitals. That means orbitals that are of the same energy level. For instance, the p orbitals, there are 3 p orbitals wherever they exist, and they all have the same energy. So one electron goes in each of those orbitals before they start pairing up. So that final line is that the electrons will fill in the order indicated in this figure. So they'll go into the 1s, then they'll go into the 2s, over to the 2p, then down into the 3s, the 3p, but before they go to the 3d, they go to the 4s. All right, and I do have an example of a worked out problem here. And this is asking for the orbital diagram of calcium where Z, the atomic number, is equal to 20. So because the atomic number is 20, meaning there's 20 protons, calcium also has 20 electrons, and we need to fill them in to these orbitals in the energy order they come in. And remember that each orbital can hold 2 electrons. So there are 2 ways to write this. One is a shorthand under the solution where it says calcium. And the other is to draw the boxes that represent these electrons. It takes a little bit more time, but I think it might be a bit more instructive. So we can put 2 electrons spin paired into the 1s2. The next, they go into the 2s2. Then we fill 6 into the 2p6s, the 6 meaning there were 6 electrons. Then we put 2 into the 3s, 6 into the 3p, and then we drop down to the 4s before we go to the 3d. We write this as 1s2, 2s2, 2p6, 3s2, 3p6, and 4s2. And one of the things that you can do if you look at this, is just that. Think about this little explanation at the bottom. Okay, now we're going to move on to understanding how this gives a periodic table the shape it has. So the 2s or the s orbitals are the first 2 rows or first 2 columns in the periodic table. So those are the alkali metals and the alkaline earth metals. Then when we go to fill the p's all the way over on the right, we call those the representative elements. They're generally nonmetals, although that diagonal of the semiconductor semi-metals will sort of cross over into that. The D's turn out to be the transition metals. So they're the part of the periodic table that is in the middle. And then the F orbitals are for the inner transition metals, and those are usually dropped down below the periodic table just basically so it fits on a page. And if we look at the actual periodic table, we see those transition metals outlined in red. So those are where the d orbitals are being filled. And then in my next slide, we can see those, the lanthanide series, which is part of the inner transition metals, are F orbitals. There's 14 of them. And then if we look beyond that, we see the actinides, which are the other row in the inner transition metals. So the filling of the orbitals helps us to see why the periodic table has the shape it has. And so one thing that you have to realize is as you go across the row of a periodic table, it always ends with a noble gas. And in a noble gas, all the orbitals are filled for that main quantum number, principal quantum number. So instead of writing that configuration where you fill out 1s2, 2s2, 2p6, you can actually just indicate the noble gas that precedes it. So in this case, potassium has 19 electrons, and so that wraps around, you have a 4s1. Potassium is an alkali metal, and so since the first part of that, the 1s2, 2s2, 2p6, 3s2, 3p6, is the electronic configuration of argon, we can just write argon in a bracket and then put the 4s1. It's just a shorthand that makes it a little bit easier to write those electron configurations. And so I have a couple of examples here where we have exceptions. And unfortunately in science, there's always some exceptions. And once we notice them, then we have to figure out what explains that. All right, so chromium, if you were to write that, you would say it has the argon core, 4s1, 3d5. However, 3d4, but instead is 4s1, 3d5. Copper is similar in that instead of being 4s2, 3d9, it is 4s1, 3d10. And the reason is because you have greater stability in your D subshells that are half filled or totally filled. So if you have enough electrons to go to a 3d5 or 3d10, it does that, leaves a 4s half filled, which is very stable. And they're very stable because you don't have that electron repulsion that has to be overcome by the magnetic force of this spin pairing of the electrons. Okay, so we're going to write the electron configuration for arsenic. It has 33 electrons, and so we're going to use argon as our core, and then we're going to fill in the additional, there are 18 electrons in argon, that's all filled. And then we start looking at the filling order for those other 15 electrons. And so it goes into the 4s, and we follow the order of these lines. And so it goes into the 4s up to the 3d and then the 4p. And so it's argon, 4s2, 3d10, 4p3. Okay, and that's it.